Hi, welcome to Finite Element Analysis with MATLAB and ANSYS. I am Kong, a postdoctoral researcher at University of Strathclyde. So thank you very much for interested in the course. And today is the first tutorial about the course, and I just want to give you basic key information about the course. So firstly, I will describe what will you learn during the course and what is the skills you will obtain after finishing the course. And next, outline of the course of course, and finally, my contact information. So what you will learn? Firstly, you will learn key formulations in solid mechanics and finite element analysis. Why I said key formulations? Because you already know that learning theory is very boring. So in the course, probably I will not explain very details in terms of meaning of physics. I just give you a summaries about key formulations that we will use during the course, and we must to remember, we must to know, because in this course we not only use ANSYS program, but we also coding in MATLAB, so we need to know the formulations. So that's the reason why I will give you key formulation here. The second thing, we will step by step writing MATLAB codes for many different examples, and we also write the input files that use for ANSYS for the same examples, right? So the first series of tutorial, I will cover 1D, 2D and 3D structure for just elements. Remember, for just element. So the example will be based from simple first, and then the level of complexity will be increased. Firstly, we will investigate 1D just examples, and then we increase to 2D and then 3Ds. Of course, we have different example for 1D, we have different example for 2D, and so on. After the first series of just element, we will go to the second series, which is 2D plate for plane stress and plane strain conditions. So in that series of tutorials, the key information also provided, and then we will try to practice FEM codes and ANSYS for 2D plates subjected to some loading in plane loading for plane stress and plane strain conditions, and with the level of the different structure from simple to more complex structure will be investigated. And finally, we jump to the third section, which is investigate 3D solid structures. And again, key formulation in finite element analysis will be provided, and then we will investigate a 3D structure, and we will try to write the FEM codes. We also try to write ANSYS input files, and we also try to extract the result and make comparison. So throughout all the example of the course, we will conduct three main activities. First, we will learn key formulation. Second, write FEM codes and run the example in MATLAB. Next, we write input files in ANSYS and run the example in ANSYS. And after that, we will extract the result from ANSYS, extract the result from our FEM code, and make comparison to verify our knowledge and coding practice. So, what skills you will learn? Firstly, when you write FEM codes using MATLAB, you will learn how to create FEM model inside MATLAB, how to import mesh from ANSYS to MATLAB for your FEM model, and how to calculate trigonometric, mathematic for 1D, 2D and 3D structures, and how to apply boundary conditions and loading conditions, and finally how to solve the equation of motion to obtain displacement fields. And after that, you will learn how to post-process your FEA results. For example, you will learn how to extract ANSYS result, how to create high-quality plots, and how to calculate stress chain in both ANSYS and in both your FEM code. When you're practicing ANSYS, you also learn, firstly, how to write ANSYS input files for 1D, 2D, 3D structures. And you will understand meaning of every single command in ANSYS. And finally, how to extract and post-process FEA result from ANSYS and then import that result to our MATLAB. So I need to clarify that why I said that ANSYS input files, because in this course I will show you a way that you will conduct FEA analysis using ANSYS by advanced level. But I will teach you from very simple steps to reach the advanced levels of conducting finite element analysis using ANSYS by writing script files or input files. You don't have to click bottom, you don't have to go through on the bottom and click and input some parameter. You will write in a text file and then just tell ANSYS to read that file to run the whole simulations. So here is the outline of the course. As I said, because this course is also cover MATLAB code, so key information is very important. We cannot avoid the theories. So from lecture 1 to 4, I will provide key informations that we must know. Of course, you don't need necessary to remember everything, but probably we need to somehow to store that formations in somewhere and we will use them later. From lecture 5 to 11, both theory and examples for 1D just element will be provided. And from lecture 12 to 18, the theories and examples for 2D just element will be investigated. From lecture 19 to 22, the theory and examples for 3D just element also provided. And from lecture 23 to 30, theory and example for 2D plate structure. Both plane strain or plane stress condition is presented. And then after that we jump to the 3D structure from lecture 31 to 35. The theory, key formations and example for 3D solid structure are presented. And after that, to summarize all the content of the course, a practical exercise will be given in lecture 36. Of course, the feedbacks will be provided up on your request. For example, when you finish the exercise, you can send me and I will view and send back to you my ideas, my comments. And finally, the conclusion about the course and the outlook for the near future study will be given. And finally, my contact informations. So even now, if you decide that you will not study the course or you still considering the course, please, if you have any questions, send me an email. I will try to answer by my best. And if during the course you have any difficulty, you have any questions, send me via this email. I will try my best to answer you as soon as possible. Thank you very much and see you on the next tutorials. Okay, so let's go to the first lecture about basic definitions. So in this lecture today, we will cover two contents, two main sections. The first one is the coordinates and displacement, and the second one is displacement gradient and deformation gradient. Although they are very basic but very important, and we will use them throughout the course. About coordinates and displacement, whenever we want to investigate a structure, so in pink in here, we need to put the structure in a coordinate system, and traditionally we often choose the Cartesian coordinate system x, y, and z, which is fixed as a coordinate system. So the coordinate, let's say we consider metropole here. The coordinate of this metropole in the undeformed configuration is represented by the vector of coordinate x0, where x0 is divided include three components: x0, y0, and z0. Now let's say we apply some loads or force or moment on the structure and it gets deformed. And here is the deformed configurations. Now the same metropole move from here to here. So this vector denoted by x1 is the coordinates of metropoles in the deformed configurations, and it includes three components: x1, y1, and z1. So the displacement of metropoles, these metropoles, is denoted by vector u, where u equal to x1 minus x0, and it includes three components: u, v, and w, where u equal to x1 minus x0, v equal to y1 minus y0, and w equal to z1 minus z0. For an example, we consider one-dimensional bar. Let's say we have a bar like this, and here is the undeformed configurations. We have some metropole located on the center line of the bar, let's say here. Now we apply some loading, tension loading, let's say, to make the bar is stretching and it's become longer. And here is the deformed configurations. So as you can see, x60 is the coordinate of point 6 in the undeformed configurations. x61 here is the coordinate of point 6 in the deformed configurations. So u6 will be equal to x61 minus x60. So that is the definition of displacement. So now go to the displacement gradient and deformation gradient. Okay, so go here, we have some word called gradient. Actually it comes from mathematical definitions. It not come from engineering definition, but it's very important. And if you want to know what is gradient, you can Google it. It's very straightforward to see the formation of gradient. But in here, I just want to highlight the formula of the terms that we want to use and we will use. So firstly, the displacement gradient denoted by h. For this character, you can put it as a character, it's up to you, but in this course we call it h. So in three-dimensional structure, h is 3 by 3 matrix including u, x, u, y, and u, z, v, x, v, y, and v, z, w, x, w, y, and w, z, where u, x is the derivative of u, displacement u, with respect to the coordinates x. U, y is the derivative of displacement u with respect to y coordinate, and so on. In 2D, we just simply take the first four components of this matrix, which is u, x, u, y, and v, x, v, y. For 1D, it becomes only u, x. That is displacement gradient. And now one more term, deformation gradient. You probably in the future, when you go some course about structural analysis, you will see very frequently the term we call deformation gradient. So it's very important. Gradient is denoted by f, but in some books maybe they use x or other characters, but it's not important. The important is the formulation of it F equal to H plus I, where I here is the identity matrix. Okay, so just go to the next one to see what is the I. In 3D, I is a 3 by 3 matrix 1 1 1 here, and then F equal to 1 plus u comma x. Here is u comma y, u comma z, v comma x, and here is 1 plus v comma y, v comma z, w comma x, w comma y, and here is 1 plus w comma z. Right. For 2D, f will equal to 1 plus u comma x here, and in this term we have 1 plus v comma y. And for 1D, it become only 1 plus u comma x. And that is all about these lectures, and see you on the next lecture. Hi, I am Kong here, and welcome back finite element analysis with MATLAB and analysis. So today we will continue our series of tutorial about finite element analysis, and we will talk about stress and strain. So the tutorial today will include 4 main sections. Firstly, strain, and then stress, and then stress-strain relation, and finally the formulation for von Mises stress. So the first one is about strain. Probably I will not give you an exact definition of strain, but here what I want to discuss is I want to give you an example, very simple example. Let's we have an one-dimensional bar structure like this, and then here is the undeformed configurations. Now let's say the bar is subjected to some tensional loading, and here is a deformed configuration of the bar. So the length of the bar is increased by an amount of delta L here. So in solid mechanics, the linear strains, you remember the linear strain is defined by that formulation, E equal to delta L per original length. And you remember that that definition is used for linear analysis, okay? And the common use formulations for linear strain is in this formula, that is in metric form, general formulation, where H here is a displacement gradient that we already covered in the previous tutorial. And you also may see some other definition of strains. You can see some term like people call two strain or hanky strain. You can heard about Green-Lagrange strain. I would say that all of these definitions are often used for nonlinear analysis, and in this tutorial, in this series of course, I will not cover nonlinear analysis. So please, at the moment, please ignore that term, right? We just focus on linear strain. Okay, so we will go further. What is a linear strain? Here is a formulation for linear strain. And if you remember, in the previous tutorial, we already covered what is the formula for displacement gradient, H. Here is a 3D, 2D, and 1D. And then now if we use that displacement gradient to substitute in that equation, what we will obtain? Wow. The linear strain tensor E here in 3D will have this form. You can see that all the components here and here, they are equal to each other. Here and here, they are equal to each other, and here and here. And in general, they are very commonly, we can write the linear strain tensor in a vector form. I call E hat here, which means the vector strain, and it equal to EXX, YY, ZZ, XY, XZ, and ZY, where XX, EXX will equal to the first term here, U comma X, E y y will equal to v comma y, which is here, and E z z will equal to w comma z, which is here. E x y will equal to E y x will equal to this term. Similarly, E z x equal to E x z, which is this term. And finally, E z y will equal to E y z, which is this term, right? If we consider two-dimensional structure, the linear chain tensor will reduce to this form, which is I only take the first four components of this matrix here. And the vector form is in this formula. We have only three components, E x x, y y, and x y. And for 1D, it becomes very simple. E will equal to u comma x, just one single value. The next one about stress. What is the linear stress tensor? Again, in this course, I only consider linear stress because this course is basic about finite element analysis. So about nonlinear analysis, which is advanced level, I will not cover in here. So in linear analysis, we only consider linear strain and linear stress. So in linear stress tensor in 3D, we have this formula where sigma xy will equal to sigma yx, sigma xz will equal to sigma zx, and sigma yz will equal to sigma zy, right? And the stress tensor can be written in a vector form, which is here I call sigma hat, which is vector, and it equal to sigma xx, yy, zz, xy, xz, and zy. In 2D, we simplify that matrix by taking only four components here, right? And the vector forms include three components, xx, yy, and xz. And in 1D, it becomes very simple, sigma equal to sigma xx. And again, note that you may hear a lot about Kirchhoff's stress, but for example, first Piola Kirchhoff's stress, second Piola Kirchhoff's stress, but that is used for nonlinear analysis. In this course again, I just consider linear analysis as a basic course, so we will ignore anything about Kirchhoff's stress. The next section, what is the relation between stress and strain? And again, I only focus on the relations for linear finite element analysis. So in linear finite element analysis, we assume that the volume of the structure, the thickness of the plate, or the cross-section area of the bar or beam are unchanged, and the rotation is small, because we base on the small deformation assumption. So we assume that when we tension the plate, the thickness of the plate is not changed, or when we tension a structure, the volume of one particle is not changed, but in fact it should be changed. But because we assume that the deformation is very small, then the changing of these terms can be neglected. So, but generally, the Cauchy stress is affected by rotation and volume change. But in the linear analysis, as I said, we will ignore all of them. And that is the assumption linear finite element analysis inherits. So, if we assume that relation, the Cauchy stress can be easily calculated by using linear strain from this formulation, where C here we call elasticity matrix, or sometimes we call stress strain matrix. In 3D form, that relation can be written fully in here. So where C matrix here for 3D is that big matrix, right? For 2D, we have two cases. If you consider in here, I have a plate which is shown in blue here. The dimension in the thickness of the plate is denoted by Lg. So there are two cases. If Lg is really big compared with Lx and Ly, we assume the plate is in plane strain conditions. If Lg is really small to Ly and Lx, which is very thin plate, we assume the plate is in plane stress condition. So in plane strain condition, the relation is written in here, where the C matrix takes that formula. And in the plane stress condition, the relation between the strain and stress is represented here, where the C matrix here takes that form. As you can see, the plane strain condition and the plane stress condition, the formulation of C are very different. And in 1D, very simple, sigma will equal to Young modulus multiplied with strain. And the next thing, von Mises stress and von Mises strain. So why we need von Mises strain and why we need von Mises stress? So in structure analysis, you can see here is a traditional graph of steel material. So you can see the behavior of structure. Here is a relation between strain and stress, right? So under some small deformations, up to here you can see the relation between stress and strain is completely linear. However, when the stress on the structure reach some critical value, and then the structure starts yielding, or it starts to have some plastic deformation, and then now the stress generation is not linear anymore, right? So this point we call zero strength, or if we take that one here, we call zero stress here. So that is very important value of material that we need to know for each material. Zero stress, or we call zero strength. Below that limit, you can see the relation between stress and strain is linear. So in the structural design, very traditional method is we will compare von Mises stress with the zero strength, right? If the von Mises stress higher, equal or higher than zero strength or zero stress, we know that okay, now in the structure plastic deformation will occur, and then now your problem is not simple anymore, it will become very complicated, right? So the von Mises stress is a value that used to determine if the given materials will yield or fracture or not, right? So in 3D, the von Mises stress is in that form. In 2D, the von Mises stress is in this form, right? So please remember that one, because in the future we will use that formulation to calculate the von Mises stress and to compare with ANSYS. I think that is all for the current tutorial. Thank you very much and see you on the next. Okay, so welcome back to the course finite element analysis with MATLAB and ANSYS. So today we will cover the lecture about the traditional procedure in finite element analysis. So the main contents of lecture today is include what is the equilibrium equation, or in other words, some people call equation of motion. And after that, we will see briefly the general formulation of stiffness matrix that we use in finite element analysis, and what is the mass matrix, and finally the numerical procedures we often use in finite element analysis. So firstly, about the equation of motion or equilibrium equation. So basically, the equilibrium equation is obtained based on the principle of vertical displacement. Okay, so I just put the reference here, which is a book from Bathe from MIT University. So they cover and explain details of what is the principle of vertical displacements. But probably I will not provide any information about that one because it is so long, and I just want to provide you as a key formulations. So if you want to see more detail, just please read that book and you will see there are a lot of useful information. So for static analysis, we have stoichiometric mutiny with the displacement vector will equal to external force, where R is a vector of external force, K is the stoichiometric of the structure, and U is the vector of displacement. So for dynamic analysis, the inertial force must be included. So we have m multiplied with u2 hat 2 dot here, which is mass multiplied with the acceleration, and plus kU equal to r. So here is the inertial force, here is a k multiplied with u, which is the internal force, and then it should be equal to external force. For dynamic analysis, including damping force, beside these two terms, we will have one more term we call damping force, where u dot is the vector of velocity and c is the damping matrix of the structure. So in this course, you may not see any example of this one or even dynamic one. So I just want to provide you key formulations, key examples for static analysis, but I'm quite sure that after this course you can do whatever you want for dynamic analysis or even for dynamic analysis including damping force. So it very easy to implement those choose equation. But the most important is how we calculate stoichiometric, how we calculate mass metric, and how we obtain the displacement field and strain and stress field. So that is the reason why in this course I will mainly focus on this one. So about stoichiometrics of the structure, let's say in finite element analysis, in order to investigate a structure, first we need to model it, and then we do meshing. So when we meshing, basically we divide the structure into many elements. So each element will have its own stoichiometrics because element stoichiometrics Ke. And then let's assume that we have n is the number of the elements in the structure. So the stoichiometric of the whole structure is the summation of the element stoichiometrics, and the element stoichiometric is calculated by using this formula. So where here B because the strain displacement matrix of the element, BT here is simply the transpose matrix of B, C here is the elasticity matrix of the element, or that is exactly the stress strain matrix that we cover in the lecture 2 and 3, and V here of course is the volume of element. So for the detail of explanation I can give you, I can show you more here. So the elasticity matrix is that one. So the stress equal to C multiplied with E. So you probably remember that one in the previous lecture, right? So B is the strain displacement matrix. So where we can represent the strain of the element equal to B multiplied with the vector U, where U here is a nodal displacement vector of the element. So for example, you can see here, let me consider a one-dimensional element I, like this. The element I including the node K and node K plus 1. So the chain of the element is in the natural coordinate system C here will equal to B multiplied with UK and UK plus 1. So you can see the nodal displacement vector U here is the UK and UK plus 1, right? Because this element includes two nodes, so this vector includes two components, which is UK and UK plus 1. So from here you can see that the B matrix for one-dimensional structure should have the dimension of 1 by 2. For four-node element for two-dimensional structure, you can see that we have natural coordinate system C and neta, and then so we have three components of chain. ECC is similar to EXX in the previous lecture. Is neta neta is similar to EYY, and EC neta is similar to EXY. And then three components that one will equal to B multiplied with the nodal displacement vector. Okay, so what is the nodal displacement vector for 2D? You can see for 2D, each node here will have three components of displacements, which is the displacement in x direction and the displacement in y direction. So the nodal displacement vector is represented in this form: u1, u2, u3, u4, v1, v2, v3, v4. Okay, so in here some people rearrange that vector to become u1, v1, u2, v2, u3, v3, u4, v4. It's not important. If we rearrange that vector, probably we need to rearrange the component inside of that matrix. So for details of that, how we calculate B, how we arrange the vectors, we will cover in the following lectures. About the mass matrix, the mass matrix is similar. It is a summation of the element mass matrix. So here ME is the elements mass matrix, and it's calculated by using these formulations. So it is a summation, integration over the volume of the element, and inside that one here is a mass density, here is a displacement interpolation matrix, transfer of it, and here is a displacement interpolation matrix, and dv here is just where v is the volume of element. So probably up to here you can see that okay, there are a lot of definitions, and I just want to tell you that just be patient. Ni here, the detail of formation for Ni for each element, I will cover it in the lecture corresponding to that kind of element. So up to here you just have a quick view and general idea how we construct all the matrix and how we solve the system. So you don't have to really worry about the detailed formation of those terms. So the last one, what is a traditional numerical procedure in finite element analysis? I would say that each person, even when you finish this course, you may have drawn out numerical procedure. It is not really fixed, but here is something I prefer. Consider that one is the recommendations for you, especially in this course, because in this course I will follow that numerical procedure. So first, we need to create the geometry. For the structure, we should know the dimension of structure and then create geometry and material properties. And then, based on your problem, if you want to simplify that is one-dimensional structure, you need to choose one-dimensional element. If you want to investigate that one in 2D or 3D, you need to choose suitable element type and then create mesh. After that, based on the element type you choose, you will calculate the shape function, and then when you got the shape function, you will obtain the displacement interpolation matrix N. Up to here, you can easily calculate stiffness matrix K and the mathematic M. After that, you now go to the next step, which is you can define boundary conditions, and by the boundary conditions, and also define the external force that you want to apply on your structure. Okay, so up to here you have mathematic, you have stoichiometric, you have external force, you have boundary conditions, so you can solve the equation of motion up to here. And then when you solve that one, you will obtain the displacement field, or in dynamic case you can obtain the displacement field, acceleration field, and even velocity field. But I just, for simplification, I just consider that one, so you can obtain the displacement field. And then you go post-processing. What we do in post-processing, we will obtain stress and strain, and we can compare stress and strain with some allowable values, and then you can give a final conclusion that whether or not the structure is safe. So that is a traditional procedures we use in finite element analysis. And up to here, that lecture is finished. Thank you very much, and see you on the next one.